Hey gang, let's look at an application of probability and specifically conditional probability. This application, I'm going to use medical testing as the example. However, this could be applied to many other scenarios, which I will allude to at the end of the video. Let's start with a couple brief definitions here. We've got sensitivity and we've got specificity. And this has to do with the testing for a disease and testing whether it is present or absent. Most medical tests are not 100% accurate, and there is a chance that you can get a false positive or a false negative. The sensitivity of a test can be interpreted in two ways, as is generally the case with probability. It's the chance of correctly detecting a disease when it is present, or it is the proportion of people who have the disease and who test positive. And notice, this is in essence a conditional probability, because first the disease would have to be present, that's the circumstance, and then the test would have to detect it. So we can write this with notation quite briefly as the probability of testing positive. I'm going to write test plus sign, given that the disease is present. And we can even represent this in another way, but I'm just going to write equals and leave a space, and we'll come back to that because we still need to introduce some more concepts. On the flip side here, specificity. This is the chance of correctly indicating when a disease is not present or absent, or the proportion of people who do not have the disease and who test negative. Notationally, we can write the probability of those who test negative given that the disease is not there. The disease is absent. And again, we can represent this in another way, but we're not quite ready for this at the moment. I'll just leave a little space there. Let's jump into this example. Suppose 10% of a population has some disease, and a test for that disease has the following sensitivity and specificity rates, 95 and 92% respectively. What we're going to do is draw a probability tree that helps us organize our work and will illustrate all the possible outcomes in this little scenario. The sensitivity and specificity are provided. That's great. Usually those are pretty higher probabilities. Furthermore, we are given information about the prevalence of this disease. That is the 10% here. That's how prevalence of the disease. So I'm going to scroll down, and in this little tree, we need to indicate, I'm going to go horizontally here, our first set of branches, whether that's going to be, is that going to be the positive and the negative test? Or is that going to be whether the person has the disease or does not have the disease? Well, it only makes sense to consider the first set of branches as dividing up the population in terms of who has it and who does not. So backspace here. So this first branch is going to organize the individuals in terms of whether the disease is present or absent. Along the branches for the tree, we need to indicate the probability of that happening in this population. That information is given by how prevalent the disease is. So since 10% of a population has the disease, that would be the chance of any randomly selected individual having the disease, which makes this other event complementary at 0.9. The next set of branches is going to branch off from disease present and disease absent. And these events here are going to represent the outcome of the test. So here I'm going to say test positive. That would be sort of a jiving situation, right? Because the test is positive when the disease is present, but it is also possible to test negative when the disease is present. Those have specific names. We'll get to that in a second. Similarly, for this bottom set of branches, when the disease is absent, it is possible to test positive, and it is also possible to test negative. But what are the values that we are going to write on these 4 branches here? Well, let's consider the sensitivity rate first. Sensitivity is the probability of detecting the disease when it is present. So that would be the disease is present, and then the test comes back positive. That's going to be 0.95 on this branch, which means there is a 5% chance that the test comes back negative even though the disease is present. Where is this specificity going to come into play? Well, that is the probability of getting a negative test when the disease is not there. So that will be on this far bottom branch, 0.92. And the branch right above it must be, careful, 0.08. So there are sort of 4 situations that can happen here, right? Because there's whether the disease is present or not, and then the test being positive or negative. So that's 2 times 2. And each of these has a name, and you might know that name. They're kind of not too esoteric. This very first scenario here, that is called the true positive, because there's a positive test result and it is in alignment with the disease being present. So that is a true positive. The one right below it, the disease is present, but the test failed to detect it. So that is called a false negative. This third one is a positive test result. However, it was positive despite the disease not being present. So that is also a false situation, false positive. Our last branch here is when the test is negative, when the disease is absent. So that is a true negative. So there's 2 trues, 2 falses, 2 positives, 2 negatives. Now that we've got all of our outcomes here organized, let's answer a question that pertains to the situation. The question is, what is the probability that a randomly selected individual from this population will test positive? Well, let's write some notation first. Probability of a test coming back positive. Well, how many ways can you test positive? It appears we can have the false positive and there's the true positive, right? So there are 2 ways. They are disjoint. We need to consider the probability of the true positive or the probability of the false positive. The word or hopefully reminds you of the addition rule. So I'm going to combine these quantities with a plus sign. I'm going to go over here, throw back to the addition rule. So we need to determine these probabilities. So what is the chance of a true positive? Like we saw in a previous video about probability trees, we want to end up at this location. To get here, we need to start at the top of the tree. Be the squirrel. Gobble up the probabilities along the way. To have the true positive, you first need to acquire the disease. There's a 10% chance of that. And then the test needs to be positive given that the disease is present. So that would be 0.95. I'm going to demonstrate this with the notation, and then we'll see just plugging in the numbers is quite easy. So to have the true positive, first, the probability of getting the disease must happen. So disease present. And then the next stop on the tree is that the test comes back positive. So that would be multiply the probability that the test comes back positive, but that is given that the disease is present. What that boils down to is 0.1 times 0.95. But hopefully that is also an illustration of dependent events that we saw in the previous video with the general multiplication rule. Multiplication rule. Okay, so that was the true positive probability. We still need to add on the false positive probability. I will spare you the notation here. Hopefully you can see what it is. The false positive probability, well, we see where we have to go on this tree. First, the disease must be absent, 0.9, times, then the test must come back positive given the disease being absent. So that would be multiplication by 0.08. And for thoroughness here, I'll just rewrite that product. but now I'm going to get the assistance of a calculator to help me compute this. Hello, R, 0.1 times 0.95 plus 0.9 times 0.08, about 16, almost 17%. I guess it's exactly 16.7%. That's kind of fun. You have to consider the possibilities associated with this question. There are two ways to test positive: the true positive, false positive. And then we used some of our previous properties and rules of probabilities to get us to the solution. So I really do believe that this tree helps organize our work and helps it to be a little bit more intuitive. Let's look at another question. This is really the money question here, because now that you know almost 17% of population would test positive, a substantive question would be, now that I've tested positive, what's the chance that I actually have the disease? So notice that this question here is about conditional probability. With the notation, we are talking about the probability that you actually have the disease, actually has disease, given that the test came back positive. It's a good question to ask. So this is a conditional probability. Reflect back on the formula for such. Conditional probability limits your sample space to this portion beyond the vertical line. Right, so we are considering only the world in which a test has come back positive. Therefore, in this division, we need to consider in the denominator the probability of testing positive. Don't we already know that answer, though? Wasn't that previously determined? So out of all possible positive tests, the question is, what's the chance that the disease is actually there? So in the numerator, we need the probability that the disease is present, but that disease being present needs to be occurring and alongside that positive test. Right, we've got that intersection occurring up here. Let's see what this boils down to. The denominator, we already know that part, right? Testing positive has a probability of 0.167 via the true positive or the false positive. In the numerator, we basically want to focus on the true positive part, right? Because the disease is there and then the test comes back positive. If we scroll up, disease there, test positive. Disease there, test positive. That is the true positive there. So that would be 0.1 times 0.95. 0.1 times 0.95. 0.1 times 0.95. That is the true positive. True positive out of all positives. We are isolating the true positive out of all positives. I'm going to open up R again to help me with this calculation. OKR 0.1 times 0.95 divided by 0.167, which is about 0.5688. I'm going to write 0.5689, which is approximately 0.5689, which is approximately 56.89%. So a reasonable question to ask upon any person obtaining a positive test result would be, well, what's the chance that it's the true positive? Because we know false positives are possible. So these values were all fictitious, however, potentially realistic. Usually for medical tests to be on the market, those sensitivity and specificity rates need to be quite high, probably even higher than this. And if you do some handy internet searching about particular tests, maybe for HIV or maybe COVID, you will see that they are quite high. I want to scroll back up to the very top of my page here and talk about another way to consider sensitivity and specificity. I had mentioned there's another way to write this and that we would come back to it. Here we are. Sensitivity, because it is the proportion of people who test positive out of everyone who has the disease, we can write that in terms of true and false positives, etc. A proportion. In the numerator, this will be the number of individuals who test positive and have the disease, so that would be the true positive. But this needs to be out of everyone who has the disease. So this would be anyone who would get the true positive or plus sign. Who else might have the disease? People who have the false negative. So that's kind of an interesting little way to write that, yeah? Everyone who has the disease would be anyone who could get the true positive or the false negative. Those individuals would have the disease. But it is the number of true positives out of everyone who could have the disease that is tested that contributes to the sensitivity. We're going to do that same little process over here for specificity. The proportion of people without the disease who test negative. So in the numerator, this is everyone with a true negative out of everyone who does not have the disease. That would be all the individuals who would test negative, a true negative. And there's some false in here. The false positive people also qualify as not having the disease. So kind of a cool little way to think about that. In the beginning of the video, I alluded that there are other applications to this thought process. And I will give you a quickie example right now. And that example is that of airport security, or any sort of security where there is usually a metal detector or some detection device that is aiming to detect weapons or some sort of danger. And in this scenario, you may consider whether the danger is present or not. So maybe danger is present, whatever that may be. And over here, I'll say not present. And then there's the detection device. And that detection device, if you've been in an airport or some other security threshold, there is the positive and the negative, right? Let's quickly discuss the implications of the true and false, positives and negatives. Well, true positive would mean that the danger is present and the detection device identified it. So that's groovy, right? And when the danger is not present and the detection device lets you walk on by without any issues, true negative. That's pretty groovy. Happy face, happy face. Let's consider a false positive. A false positive. A false positive isn't so bad, right? Because this is what happens to seemingly every other person at the security checkpoint, where your keys or your belt makes the detection device sound its alarm, and you get the pat down. It's not really a big deal. It's just a minor inconvenience. So that would be like the consequence is it's a minor inconvenience. Unless you're in a rush, oh well. Let's consider the false negative. This one's not so great, because that is when some danger is present, however, the detection device did not catch it. So that's not so good, right? Typical of these kinds of scenarios would be that we would want a high sensitivity rate, right? We want the true positive to have a very high rate, so that way false negatives have a very low chance of occurring. But sort of on the opposite side of that coin is there's generally a low specificity in this type of scenario, because the consequence of a false positive is just a minor inconvenience and it's not too detrimental. So usually these specificity rates are kind of low, which results in a higher false positive rate. We will see this again in our class in the future in the context of hypothesis testing, where this false negative and false positive have other names. This is called a type 2 error, and false positive is called a type 1 error. So we'll see that in a few weeks in our course, but that's kind of a nice little introduction to that concept. So anywhere where there is a detection of some material or bacterium or virus, you can have these true positives, false negatives, etc. Hope this was a fun application for you. See you in the next video.